Good morning, everyone. I am B. Veerakrishna, Mtech Research Assistant under Dr. Anish Sobanan. As part of my Mtech RA thesis stage 1, today I am here to present my thesis work of my first semester titled A Photonics Assisted Approach to Beam Squint Mitigation in Wideband Phased Antenna Arrays. With advancement in technology, modern wireless communication systems are rapidly evolving towards applications that require ultra high data rates, massive connectivity, high resolution sensing, very low latency communication, and high angular resolution imaging. Applications such as 5G, 6G wireless communications, autonomous driving, satellite communications, SATCOM, LIDAR, radar imaging, ISAC, integrated sensing and communication, all these require highly directional and dynamic steerable wireless links. To satisfy the increasing bandwidth demands, communication systems are moving towards millimeter wave and terahertz wave frequencies. So the enormous bandwidth available at terahertz frequencies enables extremely high data rates approaching terabit per second. So for 5G wave band, the band is from 30 to 100 gigahertz, and for each channel, the bandwidth is 1 to 5 gigahertz. Now, for when it comes to terahertz band, it is extending from 100 gigahertz to 10,000 gigahertz, and bandwidth is from 10 to 100 gigahertz. That is tenfold, 10 times the 5G wave band. So with this, we are aiming to get terabytes per second single user data rates in 6G. Among these challenges, free space path loss becomes extremely severe at higher frequencies. We know that when an antenna radiates electromagnetic power, the energy spreads over an expanding spherical surface. Here, free space path loss represents the attenuation of the electromagnetic waves due to geometric spreading in free space. With increase in frequency, the effective aperture of the receiving antenna decreases. So the receiving power at the receiver end decreases with increasing frequency. Now, free space path loss increases with uh, the distance between the receiver and the transmitter and the operating frequency, and relation is given by this equation. So it is clear that higher frequencies are prone to more loss. Therefore, high directional antennas and beamforming techniques are very essential to maintain reliable communication systems. One more challenge in terahertz communication is scattering. Scattering refers to radiation of electromagnetic energy caused by the interaction with the material inhomogeneities. Consider a particle with size A and consider the signal with we are transmitting or receiving is having wavelength lambda. Now, depending on the particle size and the wavelength of the signal, there can be two types of scatterings. One is Rayleigh scattering, when the particle size is much lesser than the wavelength of the signal. And other is scattering, when the wavelength of the signal and the particle size are comparable. We know that terahertz band is from 0.1 terahertz to 10 terahertz. Now, for this band, the resulting wavelength range is from 30 micrometer to 3 mm. It was found that atmospheric particles and surface irregularities are having particle sizes comparable to the wavelength. Therefore, scattering at terahertz frequencies is scattering. Scattering at terahertz frequencies. This is a simple diagram to illustrate how energy is scattered into multiple directions and how propagation loss is increasing. Therefore, using high directional antenna arrays, we try to form a beam in a particular direction and try to steer that formed beam towards our desired direction. So beam steering is nothing but directing the main lobe of the antenna array towards a desired direction. With this, it reduces the interference in undesired directions. It will increase the signal strength. It will improve the reliability and can compensate for propagation losses. Now, we'll understand how can we form a beam. That is, we will study about beam forming architectures. Beam forming is nothing but concentrating energy towards a desired direction. And this is very much essential for high frequency communications. So it can compensate propagation losses. There are three main beamforming architectures namely analog beamforming, digital beamforming, and hybrid beamforming. And there are some trade-offs between hardware complexity, bandwidth, power consumption among these beamforming architectures. So beamforming is nothing but concentrating the analog beamforming. It performs beamforming in the RF domain using analog phase shifters. A single RF chain feeds all antenna elements through a network of power dividers, phase shifters, RF feed lines. And some advantages of analog beamforming include low power consumption, less number of RF chains, lower implementation costs, and lower hardware complexity. Since only one RF chain is required, analog beamforming is very much advantageous for large antenna arrays. And it is very much suitable for narrowband systems. However, there are some limitations of analog beamforming. One of the major limitation is that it is not suitable for wideband communication systems, because in wideband communication systems, this analog beamforming suffers from a phenomenon called as beam squint. Digital beamforming. It performs beamforming in the digital baseband domain. Each antenna element possesses its own ADC and DAC mixer, RF chain, and baseband processor. Each antenna element can independently control the amplitude, phase, and the delay. So it supports MIMO and adaptive beamforming. And there is one RF chain per each antenna element. It is very much flexible for large multi-user MIMO systems. And that's why it is advantageous for adaptive beamforming. In this beamforming technique, the beamforming weights can be updated dynamically using signal processing algorithms. So it is also having good precision. And there are few limitations of digital beamforming, which include larger power consumption, larger chip area, higher hardware costs, and difficulty in synchronization. And there are also thermal management problems. For massive arrays containing hundreds of antenna elements, fully digital beamforming is really impractical. Hybrid beamforming. It combines both analog and digital beamforming. Here, a smaller number of RF chains are connected to larger antenna arrays through analog phase shifters. Hence, the hybrid beamforming is having advantages like reduced RF hardware complexity, lower power consumption, good scalability, and multi-stream transmission capability. This hybrid beamforming will offer a compromise between analog and digital architectures. And limitations of hybrid beamforming include beam squint. As we are using analog RF stage, that is, we are using phase shifters, therefore beam squint is inevitable. And also array gain decreases, and terahertz beam alignment sometimes become inaccurate. Therefore, even hybrid beamforming still faces limitations in ultra-wideband terahertz communication systems. This is a comparison table of various beamforming techniques, where we can see that in digital beamforming technique, there is no beam squint, and it is very much suitable for terahertz communication systems. But as we see that it is having a lot of receiver complexity and high power consumption. And analog beamforming is a simpler one, but it suffers from beam squint. And hybrid offers a compromise between these two, but still it suffers from beam squint. Now we understood that beam forming techniques would be useful for terahertz communications. Now with the help of simple uniform linear array, we'll understand how beam is forming and how can we state that beam form. Consider a uniform linear array having n identical antenna elements which are spaced by distance d, and these array radiates electromagnetic waves into free space, and depending on the phases, the fields may add constructively or destructively. So this constructive and destructive interference of the radiated waves forms the beam in far field. To form a beam, the geometry of the antenna array is crucial. That is, if we space n number of elements by some distance d, so towards broadside it will form its main beam. Just by spacing two antenna elements or more than two antenna elements, we are able to form a beam. Because when two antenna elements are spaced by some distance d, it creates a path difference of d sine theta in far field. And because of this path difference, uh, propagation phase difference also exists. With elements spaced with the distance d, the propagation phase difference is given by 2 pi by lambda times of d sine theta. Now we have formed a beam just by spacing two or more than two antenna elements with some distance d. Now our aim is to steer the beam towards our desired direction. We told that when we place elements at some distance d towards the broadside, as there is zero path difference, our main beam is forming towards the broadside. Now we want to steer that beam towards some direction other than broadside. So to steer that beam, we need to, without moving, we need to steer that. That is, to steer the beam electronically, we should be exciting each antenna element with some progressive phase shift beta. And the resulting antenna factor is given by this equation. The antenna factor will determine the directional radiation pattern of the array. We are having two things here. One is radiation pattern due to single element and radiation pattern due to array factor. That is because of the geometry of the antenna array. So the geometry will decide the beam forming, and the excitations given to the geometry of antenna array can decide the direction of the main beam. Therefore, by controlling the excitation phase, the beam direction can be controlled electronically. Now, to steer a beam towards our desired direction, we need to make sure that the fields due to the all the antenna elements will constructively interfere at our desired direction. To make sure that all the fields will interfere constructively towards the desired direction, we need to make sure there is no path difference towards that side. But we fixed our geometry. That is, each element is at a distance d from other element. So we cannot change this distance. So electronically, if we are able to compensate the phase difference at our desired direction, then we can get maximum radiation towards that direction. Therefore, if the total phase at our desired direction theta becomes zero, that is when zero somehow, then we can get the maximum radiation towards that direction. So we are having phase shifters. So we are having beta, our excitation phase, which we can give to our antenna elements. So the progressive, the phase difference due to geometry, when it is compensated by the excitation phase given by us, then we can get constructive interference. Therefore, we need to give excitation phase, which is equal and opposite to the propagation phase. Hence, changing beta will change the direction of the maximum radiation. In this way, the beam can be steered electronically without physically moving the antenna. This is a simple MATLAB result showing with increasing number of elements, our main lobe or the maximum radiation is getting narrower and getting more directed. And this is a radiation pattern of 9-element antenna array with beam steering. We can see that we are able to move the main lobe by our desired angle theta. Hence, this electronic beam steering is good for only narrowband communication systems. When it comes to wideband communication systems, where there are multiple frequencies, this single single frequency dependent phase shift may not help us get a main lobe towards our desired direction. Therefore, whenever we use fixed phase shifters in analog beamforming and hybrid beamforming, inherently inherently we are designing it for a single design frequency. When it comes to wideband signals, these beam directions will become frequency dependent. This frequency dependent nature of this frequency dependence is the one which is causing a phenomenon called as beam squint. Now, what exactly is this beam squint? and when does it occur? We know that the propagation phase depends on the frequency of the signal which we are radiating, but our excitation phase beta which we are giving to phase shifter is fixed. This imbalance will shift the desired angle condition to some new angle which is frequency dependent. Simply, different frequencies will experience different effective delays which causes the beam to squint from our desired direction. This is called as beam squint, and the relation and the angle towards which beam will squint can be given using this equation. Now, for for the frequencies which are lower than the design frequency of the phase shifter, our phase changes very slowly. Therefore, beam will shift towards end fire. And for higher frequencies which are greater than our design frequency of the phase shifter, phases will rapidly change. Therefore, our beam will shift towards broadside. This is a simple beam squint visualization result from MATLAB, wherein 2.4 gigahertz is our center frequency, or the center frequency, that is the reference frequency of the given to the phase shifters. Now, when we radiate a signal which is having 2.2 gigahertz, and when we radiate a signal which is having 2.6 gigahertz, less than or more than the center frequency, we can see that our main lobe is shifting. Yeah. Similarly, this is a MATLAB result which is showing polar view of the beam squint for three different frequencies. This is a simple radiation performance comparison wherein I have simulated a single microstrip patch antenna and a 9-element microstrip patch antenna array. And we can see that with increasing number of elements, the main lobe becomes more narrower and more directed. We told that with phase shifters, we are getting different time delays for different frequencies. Therefore, somehow, if we are able to make sure that each and every frequency will be delayed by same amount of time, then we can get maximum radiation towards our desired direction. Therefore, true time delay is a element with which we can delay the signal by fixed amount. That is, we will be having same time delay for all the frequencies. Therefore, when there is no frequency dependence of the phase, then the all the phases will add constructively towards our desired direction, eliminating the beam squint. Now, delay can be achieved by two ways: electrical and true electrical and true light. Now, this utilization of true time delay will be useful for our wideband and wideband arrays where there won't be any beam squint. In RF domain, true time delay can be implemented using transmission lines, switched delay lines, distributed LC networks, and surface acoustic wave and bulk acoustic wave devices. Now, radio frequency true time delays. These are very bulky, lossy, and these are power hungry. So more the delay, more the physical length required. Therefore, more the complex routing would happen. And with increase in frequency, the loss increases and delay also increases. And there is a phenomenon called there is a effect called as skin effect. That is, with increase in frequency, the current will come, the alternating current will confine to the surface of the conductor. Therefore, the skin depth decreases. Due to this decrease in skin depth, the resistance decreases because the effective area through which the current passing is only confined to the surface. As a result, attenuation will be increased. And this can be linked with electromagnetics, uh, in which we say that the effective inductance becomes frequency dependent for higher frequencies, and it will alter the current distribution and the magnetic field linked to that. As a result, even the group delay even the group delay becomes a function of frequency, because as beta is also frequency dependent now. Therefore, the this will distort the signal which we are trying to transmit, and hence causing dispersion. And also with increase, if you want to scale this frequency dependent loss, dispersion and power consumption will increase multiple fold. Therefore, we need an element where there is no skin effect and where there is minimum loss. Therefore, photonic true time delay is the one through which we can have nearly zero propagation loss, because we know that light is having the highest speed, and as a result there will be less latency. And with higher frequency optical carriers we will be having more bandwidth in the sense we can have more data rates. Therefore we can achieve terabytes per second data rate. And these photonic TDs can be implemented using optical fibers or waveguides. As we are using light, there will be no losses and no skin effect. However, there will be some insertion losses and power consumption, because optical fibers do consume more power. And this is a bit costly and complex, but this is best suited for terahertz and 6C massive MIMO arrays and radar applications. And we can also leverage integrated silicon photonics, where bulky optical fibers can be replaced by integrated silicon waveguides. Therefore, we are moving towards an approach where we use photonic elements to reduce the loss and avoid this beam squint. Thank you. Yeah, I have followed the below showed references. For antenna theory, I have gone through the standard textbook of Balanese, and to understand the different beamforming architectures and terahertz bandwidth, I have gone through the papers, and finally I have arrived at photonic two-time delay techniques for wideband phased arrays of NTT Nguyen, which is a good IEEE photonics journal. Thank you.